All right, so like Dr. Goley said, I'm Dr. Heck, lab director over at Dunwoody. A little bit about myself, just so y'all know where I'm coming from. Even though I say y'all, I was born in Phoenix. The other southern states. But no, I was the first lab director of Dunwoody, working with Dr. Burdett and Dr. Goley back in 2009 when we started. I was the original person to fill out the paperwork to the state of Georgia and to CMS. I subsequently left and went back to Arizona in 2013 when my dad was diagnosed with terminal cancer. So like Dr. Goley says, cancer affects everyone. I'm a true example of that. I've had, in addition to my father, other people die in my family of cancer. Then I ended up getting a phone call to come back in May of last year. I was at Arizona State doing as a research professor. And so they asked me to come back, and here I am. So I've been back in Georgia for about a year and a half now that I've been back with the company. And so Dunwoody is a very true and dear venture to me, because as one of the founding plank owners of the company, it's personal to see it go through its ebbs and flows of business. And as we increase profiles and things of that nature, it's the fun part for me is the intellectual side of looking at the immune system, what test is important, how do we then pass on that information to you guys, but also to clinicians so that they can better diagnose. Because like Cheryl always says, to me, it's a tube of blood. It's got a barcode on it. I know nothing of the patient demographic when it comes in the doors. Beyond that, it is somebody. It is somebody's parents. It is somebody's kid. It is somebody's teacher. It is somebody's whatever or another. So to us, even though in the lab point of view, and I try to remind people of this, that it's not just a tube and a barcode. It is, in fact, a person. It could just easily be your mom or dad or anybody else. And so with that in mind, it's actually interesting being from academics trying to breaking into clinical sciences it's totally different. Not only with the regulatory side of things, but there is a personal side of it, even when you're doing clinical research. I was involved in clinical research with the Mayo Clinic in Arizona, and it's a totally different scenario. They just send you things in the mail and say, here, do what you do with it. Well, and then that's as far as it goes. There's usually no reporting back to patients. There's no follow-ups. There's no anything like that. It's just you get a sample, you run one test, you get a piece of data, and then that goes on into the data set for analysis. So clinical science is a lot more fun. My PhD is in microbiology. And so the generic joke that I have is I like germs. To me, that's the fun stuff, is infectious diseases and immunology. So this is a good place for me to be as we're trying to become one of the top leading allergy labs, I guess, in the country with what we're doing. And so with that, I'm going to spend probably most of the time talking about the 588G, the comprehensive test, the 588E and G, which probably most of you are probably the most interested in, and then either tomorrow or Thursday, if there's time, we can go into methodology of the IBAs and the other testing that we do. So the method that we do is an ELISA. I'm left-handed, so I do draw on the board right-handed. It's actually more legible that way, so figure that one out. Let me know if that's too small. That's the complaint that I got when I was teaching at school, is that my handwriting is too small. So just speak up. It's called an ELISA. A lot of times you'll also see EIA, which stands for enzyme immunoassay, which basically means we're taking an enzyme, putting it into an immune complex, and generating a chemical reaction of some sort. They're non-descriptive terms for a reason, because they can be applied to everything and anything that we do at Dunwoody. So what we do on the food test is, if this is, I wasn't going to bring over a 96 well, but I'll show you. Everything that we do is in a 96 well plate. It's about that big, and it's got 96 wells on it. Each well is individually coded with an antigen. I'll draw it as a little A. So these are an antigen is anything that your body's producing an immune response to. For the food, it's apple, almond, gluten, wheat. It could be hepatitis, it could be streptococcus, it could be anything that elicits an immune response is called an antigen. And so for here, on our case, it's a food. And so you coat with an antigen. We do all of this in-house. Everything, so the materials and reagents all come to Dunwoody. We have a person specializing in coating. Dr. Clark's been with the lab for 4 years, so he's really good at his job. And so then is what happened. So the interesting thing is then you add, so this is great. You have a dish that's got this antigen on it. You take the patient sample, we send it to the lab, and then we add the patient sample to the dish. So this would be the patient sample. And in this case, it's an IgG or IgE. So it doesn't matter what the test is. So then you have the antibody. The patient antibody will stick to the dish. You know, the way an antibody will counteract an infectious agent, whether it be the food or a bacteria or virus. That's what antibodies do. They bind this stuff. We just happen to be doing the same chemical reaction in a dish. Fun with science. And so you have the patient sample, and then we can come back, and then we actually will come back with a detection to the patient sample, which I'll draw in red. It's another antibody that's got this enzyme on it. This enzyme is where the enzyme comes from. Immunoassay, immunoglobulin. It's an assay for immunoglobulin. So that's why they're collectively called an EIA. So in a brief nutshell, and then this is probably should. AB is the abbreviation for antibody. So you have a detection antibody. We say we do an ELISA. Most people will be like, great, it's an ELISA. Other companies like Immunocap, things of that nature, same technique, the same basic principle. They're just doing it in an automated machine on a particular, it's basically a metal chip instead of a plastic dish. So it's the same procedure, they're just doing it automatically. We do it in-house. So you have the detection antibody, the patient sample to a food. The thing that allows our ELISAs is automated machines are expensive, they're large, and they tend to be persnickety. They like to break down, they're affected by temperature, humidity, a little bit more. This assay, because we do it in-house, is a little bit more robust. It's not as dependent on things. But the important thing is that whatever we want to detect, all we do is change this detection antibody. So in a sample, you have an IgG or an IgE. That same patient sample also has complement, if we want to look at the complement side. All we do is detect complement versus the IgG. We can detect IgE. So just by changing one reagent allows us to totally change the results of the test. That way it also adds the reproducibility into the sense of once our technicians are trained, they know what to do because all they're doing is changing basically one reagent throughout the process. The times will change a little bit and the dilutions change, but for all intents and purposes, it's the same process. And the coding, it's the antigen. Apple is apple. It goes on all the plates as apple. So in that sense, it simplifies things, and you don't have to constantly be changing reagents. You're not changing materials. And on a side note, I mentioned the technicians. All of our technicians, and this is a federal law, actually we supersede the federal law in the sense of we have everybody in our lab has at least a bachelor's degree. Out of the, I believe we have 13 right now. 4 of them have masters in biology. I have a PhD. Dr. Clark has a medical degree. So we are actually, not only well educated, but we're technically sound, obviously, in what we do. And that's why everybody's got a hard science background in biology, chemistry, or equivalent. Because we have some people with environmental science. No, everybody's some form of biology or chemistry. So any questions over what an ELISA is and what it's useful for?
Do you have to use a new plate when you change the reagent?
Yes.
So you have like 4 plates?
No, we do.
Yeah.
And so for the food test, because the food is actually 4 tests, as we refer to them. And so you have a total IgG. You have complement. And these are the 588G. And then you have IgE. And then IgG subtype 4 is the 588E test. So because there's 4 different tests, we run 4 different plates on every patient. And ultimately, every patient sample for these 4 plates gets diluted a total of 6 times. So to make it work. So it sounds like a laborious process, but it's really not that bad. We do have automated, pipettes and things of that nature to help the process. So it's not one person doing, when we're running 60 samples, doing 240 dilutions in one day. It only takes them about a half hour. So it's where we could automate, we did automate to simplify things. But the problem with automation is that it's usually slower. And so any other questions? So we do actually run all 4. I just drew a general example. And this is where I said is the plates are ultimately coded in the same process. We change based on the plating. The only difference is 2 wells. 2 out of 96 wells are different between the 4 plates. They get different patient dilution samples, but once again, pretty much the only difference is the detection antibody. And you'll see, maybe not the entire process, but kind of hopefully can gather what's going on, depending on where they're at when we get there. Any other questions about? So that's the process. Because we do it in-house, the question becomes, well, how do you know a person is allergic to almond? I always pick on almond because it's the first one on our test. It's on a 96 well plate, all the things are numbered and labeled, and almond's the first one. And so I always pick on almond. So how do you know somebody's allergic to almond? Because this is an in-house test, we actually over quality control from what the CMS regulations say. CMS, Health Human Services has their guidelines that say this is what you have to do minimally. We do above and beyond that. Just because, like I said, it is an important thing because if we come back and show that somebody's negative for IgE, then they go and eat almonds, have anaphylaxis, the lab is legally responsible. So we have to be sure that somebody is truly negative when we report negative results. So the quality control side of this is where I spend a lot of my time. And so for the quality control, if we have our individual ELISA plate, like I said, and so there's 96 wells on a plate. 2 of those wells are quality control. Actually, 4 of them, technically, are quality control. We have 2 different blanks. And the reason the blanks are there because every time you're using a piece of equipment, you have to standardize that piece of equipment. So you have to know what the background, reading of that plate is. So the plate by itself, the piece of plastic that it's on has an absorbance in the spectrophotometer of X. So we have to subtract that out just to standardize the machine. So we have 2 blanks, but we also have 2 controls. Got to have a high control. How do you know what a positive control? How do you know what a positive reaction looks like? So we have a high control, and same thing. How do you know what a negative looks like? So we have a low control. And in all of our cases, this is one of the things that in the laboratory, if these controls don't behave the way they're supposed to, the laboratory rejects the sample outright. It doesn't make it to reporting or even quality control. They just get the laboratory writes it up as a corrective action that sample X got rejected because of this. It'll be reran tomorrow. And that's kind of the end of the story for that. And then it gets reran tomorrow, and then we'll see how it goes. So that is one thing that we do on each plate is we have blanks and controls. Another thing that you have to do is you have to have a standard. Have to have standards. This way, am I in the way? Or, oh, sorry. And the other, so the standards are there is because if a patient is reacting, I mean, you can see it on the eye, it's got a little bit of color change. Well, how much is a little? To us, it's a little. That one's got more. But for the assay, because we have blank standards and the controls, we can actually quantify, and that's where we come up with the class reactivities, is based upon the wonderful world of Excel and computers. We put all this just gets cut and pasted into Excel, and it's and generates the reports that has the patient quantifiable values, and then we put that into the lows, moderates, and highs that you see on the patient reports. And so the plate in itself is considered to be one individual, basically from a scientific point of view, it's one individual experiment. It has everything that you need to do an experiment. It's got your controls, it's got your standards, it's got your blanks. Each plate is independent of the other plates that patient may see. And the way we have our system set up, we have basically two teams. The reason I drew it this way is because we have one team that does the 588G. This is predominantly what they do all day. The other team will do the 588E, which pinpoints to us that if there's constantly a problem with a plate, we know who to go yell at. But that's just, from a human point of view, it also provides specialization. They get really good at their job. And then that way they can just do what they do and they don't, are comfortable in their job doing what they do to provide the best patient care. Another thing that we do is, like today, I think we're running 56 samples, patient samples. And the reason the magic number is 56 is because then for each batch on each day, we have 4 batch controls. So these are run on every day. So every plate has its own controls, but we also have the control for each batch that gets run for every day. The first thing we have, like on a plate, on the normal plate, is you have a quality control serum. And we have 2 of these actually, 2 quality control serums. The quality control serum is the same sample, it's plated twice, at the beginning of the run and at the very end of the run. So for example, if we're running 60 plates, like we are today, this would be plate 1 and plate 60. And if your control plate doesn't behave the way it should at the beginning of the run or the end of the run, then we reject the run because it's supposed to be consistent throughout the course of the day, because you don't want a patient that's on plate 3 to have different results than the patient that's on plate 7 and then 57. You want that difference to be the actual patient sample, not the way the assay is being performed. So we do a batch control. Similar to the plate, we also have 1 high control and 1 low control. That way we know what a high looks like across the entire plate and what a low looks like across the entire, because here is what we're doing here is we're looking at a high and a low control for all 88 antigens. So what this allows us to do is QC all 88 antigens. This does several, so throughout the entire process, this allows us to evaluate whether the technicians performed the test accurately, that all the reagents were diluted properly, things were added in the right order. This allows us to say that they did everything not only in the right order on each plate, but how the system is performing on that day. And if your positive control doesn't work, then we reject the run. If the negative control doesn't work, we reject the run. And then everything just gets reran the next day. So we do, like I said, we over quality control this because it is an important test. Because if somebody is, in fact, like it's coming back negative for almond, and they eat almonds and develop anaphylaxis, the laboratory is liable. So throughout the course, we keep track of these all day, every day. We have trending data to show that things behave, not only how they behave today, but over the course of the week, over the course of the month, and over the quarter. Because by doing that, that shows that our assays are performing the same over different lots of antigens, different plates, different technicians running different results, as well as weather. Because, and that's one of the things that we have to do too, from a quality control point of view, is we have to keep track of the temperature in the room. You may say, okay, the room's a little chilly today, or it's a little warm today. That's what we feel, but to an assay such as these, temperature matters. And so our room we only have about a 5-degree window of what we're allowed to operate in. And if the room, for whatever reason, if we lose air conditioning that day, we have to stop the run and reject it and wait till the next day, until the repairman comes out. I say that because it has happened. We have lost air conditioning, or we've lost heat. We had a Hurricane Irma, all of our refrigerators. We lost power in the lab for 16 hours about that. We have temperature gauges on all of our refrigerators and all of our freezers. And we can go back and show an inspector or anybody else and say, no, your patient sample did not, in fact, thaw in that 16 hours. It warmed up. I say warmed is the relative term because we store our patient samples at minus 80 Celsius. It's colder than dry ice. So when I say it warmed up to about minus 40 Celsius. Your freezer at home is basically 0 Celsius, so it's still 40 degrees colder than your ice box at home or freezer at home. So to say that it warmed is, like I said, a relative term. And, same thing after the storm. We had to quality control or verify that all of our materials and reagents and everything performed, and then we can go on to testing. So we do have environmental controls. We have had thunderstorms that we lost power in the middle of runs. You just throw up your hands and say, it is what it is, and kind of clean up and come back and do it again the next day. So any questions over quality control, what we do on the food test? Any?
I have a question.
Okay.
I've had a couple of patients or doctors come to me and say, okay, well, I flagged for lettuce, okay? Well, there's how many different types of lettuce? Is it all lettuce, or is it romaine? Is it arugula? You know what I mean? It's and then there's the same thing with potatoes or sweet potatoes.
Yeah, because I know we have white. Yeah.
Species list on the website. And
Oh,
find out exactly what we're looking at.
Okay.
And then to compare it to other things in the same family.
Okay.
Generally how we would treat it.
All right. 'Cause I had no idea that answer. I said that's
Yeah.
a great question.
I can show you where it is.
Okay, that'd be great. Thanks.
Yeah, and along those lines, as far as the antigens go, has anybody here done an actual skin test for allergies? It's a lot of fun. We use the same antigens at physicians, the same manufacturer, that are used on the skin test are actually used on our test. So the only difference is instead of obviously exposing the patient's skin to it, we expose the blood to the antigen. So it's essentially the same process, using the same antigens. So that's where the species list is important, is identifying lettuce versus white potato versus sweet potato.
So you mean the actual specific source? You're sourcing the antigens from the same place that the RAS test would get?
Yeah.
Okay, so for those providers that get all hung up on, is this GMO and all that kind of
Yeah,
stuff?
and then for those clients that are familiar with ImmunoCap, they won't ever tell you this on the ImmunoCap website, but if you go into PubMed, the scientific repository of all scientific literature, and you read the journal articles from ImmunoCap, they say they came from the same source that we get. So, the difference is, depending on where the journal is, it would say, this company's distribution center in Germany versus ours comes out of, I think, Texas or Oklahoma. So, but it's the same company, same manufacturer. They just have different distribution centers that the antigens will come out of. Sorry.
In terms of like submitting a sample, we say no frozen samples will be accepted.
Mm-hmm.
You freeze the patient's sample, so why can't they submit frozen?
The main thing is, because we know the samples are stable. We've done stability studies. We know they're stable being refrigerated or just shipped ambient. You know, I say refrigerated because they got the little freezer brick. The main difference is in the lab, we get the 5 ml vial in or whatever they ship. First thing we do is we take that vial, accession it, aliquot it into 2 samples. And if it's frozen, then we have to thaw it to aliquot it, or we thaw the entire 5 mils and use it and then have to refreeze it. So by splitting it into the 2 samples, we run it once. If things need to get rejected and reran for some QC point of view, we have the other vial in the freezer. So that's our, and then we have the initial shipping vial for whatever reason if we really need to go into that and that one. So we'll get a sample today, we aliquot it, everything gets frozen today. And so everything is frozen, and then we can, if needed, go back and pull that initial. That's where we say, you know, we want 2 vials. Theoretically, we can get away with 1. But if we have reruns, we want the extra vial there as our backup. And then for whatever reason of power outages and, you know, if we have to rerun things a second or third time, then we still don't have to call a patient and ask for redraws. So, which is pretty much a laboratory standard of if you know how much you need, basically at least double it so that you don't ever have to ask for another redraw. And I think in the 1.5 years, we've only asked for, 3 or 4 redraws, and that was due to other extenuating circumstances. But
Doesn't it also prevent us from going through multiple freeze-thaws?
yeah, because because like, you think about it, everybody, have you ever taken like a piece of meat out of the freezer? Or you go to the supermarket, you buy a piece of meat, you put it in the freezer, you take it out, let it thaw, put it back in the freezer, you take it out, put it back in the freezer. It's not, its texture is not going to be there. Well, it's because the proteins are breaking down. And blood samples, I mean, antibodies are all made out of protein, so they do actually break down with multiple freeze thaws. So that's kind of where we want it to come in at a thawed sample. We freeze it, we thaw it 1 time.
The only time doctors want to freeze is if they want to do a draw on Friday, freeze it over
Yeah,
the
see,
weekend
but
so they
yeah.
can ship it on Monday.
Yeah, but we know that the sample's stable in the refrigerator.
Oh,
So if they have a refrigerator, they can just draw on Friday and put it in a refrigerator until Monday and then ship it Monday. So it'll be here Tuesday.
So I may have missed this, I mean, I apologize to repeat. If they are open on Saturday and ship out that day, so it's in transit, is there anybody do a session on Sunday?
No.
Okay, yeah, on Saturdays you do that?
No. We've done this. That's one of the things that we have to do, obviously, when we come out with a new test, is we have to do stability studies. We know the samples are stable at 4 degrees, refrigerator, sorry. Science nerd, everything's done in Celsius. So just your standard everyday refrigerator is stable for, 21 days. So basically 3 weeks, kind of although we don't, and that's where our quality control policy is that any sample over 21 days, we just automatically reject. Because we also, we do get the business side of, they'll draw, the patient's like, well, I don't know, let me think about it, but they got the blood sitting in the refrigerator, it's already been drawn. So they don't have to bring the patient back. So that's one of the things that do happen that leads to things being sat for a while, but some of our clients also will batch ship. They will only ship to us on, say, Thursday. So they'll draw an entire week's source of blood and then ship it all in one day.
So should we tell people not to ship on Friday or Saturday?
Ideally it's, because we don't know what happens to that sample in the 2 days. Like I said, I'm from Arizona, and if it's sitting in some cargo container at FedEx, it's 118 degrees on the tarmac. Granted, it's probably not sitting there, it's probably sitting in an air-conditioned building, but still, or if it's already been loaded into a truck on that day, then the truck is sitting at the, FedEx yard for 2 days. So that's, that's my Arizona in me of, but it's 180 degrees in that truck. People go, oh yeah, I think so, I guess so. Flip side is now we're approaching winter time. It has happened in the past too, where we've had the ice storm here and they had to close Hartsfield, which meant no FedEx or UPS flights were landing. But then again, and so, you can't account for nature. But we also do know that samples are stable at room temperature for a week. So they're stable in a refrigerator for 3 weeks. If they're frozen, they're stable for pretty much indefinitely. If they're frozen, we only hold them in the lab for about 2 months. Because by then somebody will say, oh, can you run this test on it? We're like, well, that's how your patient looked 2 months ago. So, but we also, but yeah, so we know that our samples are stable. And if it's in the wintertime and it's stuck in a FedEx truck, it's like, well, it's 30 degrees. It's kind of like being frozen. Are there any other questions? So that's where our stability on our SOPs come out from, is ideally hold the sample on Friday, ship on Monday, but they are stable if you were to ship.
So you're saying, in a situation where like they were to say draw on Friday, they say the patient can only come in on Friday, they can draw blood, put it in the fridge until Monday?
Yeah, so draw it, spin it down, transfer it, and then overnight it on Monday. So that would be the ideal.
That's like in a specific situation.
Yeah, no, because a lot of times people do that. They'll take a half day, or they'll take a Friday off, or some people work,
Okay, all right, thank you.
Are there any other questions?
Is that the yep, or you?
I think so. Just Q&A. I was a lot faster this time. I'm getting better at the third time I've done this. Like everything else, you just hit the high points. Oh, and the other thing I should probably point out is I look at every report that comes out of our lab. I actually do physically look at every report before it gets signed out. And then it gets up. Once I approve it, then reporting will then upload it. And because part of the thing is, even though all of this may make sense and pass the plate, sometimes you just got to look at it and go, does it make sense that somebody's pretty much got high reaction to everything? I know I'm one of them people, so it is in fact possible. So I am our positive control for gluten in the lab. So
What's the average number of tests per day that you're running? Tests.
it depends. Our standard run is the 56, just because 60 is kind of our magic number, but it's kind of what we're doing right now. We can easily double this for production. So, and that's what the staff that we have, the equipment we have, the procedures we have. We can easily double without having too much of a shakeup in. The only thing that may increase will be our inventory of ordering supplies that we may have to catch up on with some of our vendors if we were to catch a sudden increase. But we seem to be having, most critical things we have a standing order, which means they have like October's order but they also have November's order. So if we needed to, we can call them up and say, hey, can you ship us half it, right now? And they usually have it. So, but from a standard point of view for the foods, this is pretty, not optimal, but that's just kind of standard that our team is doing. And
the name of the company where the reagent is coming from?
for the antigen,
Yeah.
it's a ALK.
A-OK?
ALK, Alk-Abello. Technically what it stands for, but the bottles say ALK on it. They saved on printing.
Now, you may have answered this question earlier, but I still get this question on specificity and reliability. Do we have some?
Cheryl keeps pestering me to write that.
I have a couple doctors that ask about that too.
Yeah, I need to write that. I have, yeah. It's really my fault that it hasn't been written up.
We needed it yesterday.
I know, we need, everything is needed yesterday, and I have, actually next Friday, I will be in San Antonio for my certification test in diagnostic immunology, so it's kind of the, let's get through the test first, and then, you know, all the other things that you've kind of put off for the last 6 weeks of now, all have to be done today. But yeah, we do have some of that, and I have it in the raw data form. I haven't actually just written it up nice and pretty. Like I have to get with Cheryl and figure out exactly how much detail she wants, or because she talks to you guys, so she's the one that will dictate to me what I actually write up. As far as, you know, I can write it up into a one-page blurb. Do you want data? Do you not want data? You know, it's those kind of details that still haven't been really discussed yet. So, but because I know legally we are supposed to make our information available, and not only from a marketing point of view, but if anybody were to ask.
And how about, the GMO and, organic, antigens? So where are we at, do we have a list of ones that aren't organic, or are there very few that aren't organic? Where do we
Do you?
stand with that?
I spoke with Alcabello about that, and they basically said that it wasn't really clear, like.
Yeah, because it's a local source, I think is what they call it.
Yeah, it's just a local source. And
Yeah, so.
it wasn't really clear about whether they were, like, organic or GMO.
Yeah.
Can you say that again? I couldn't hear.
I spoke with Alcabello, and they weren't clear, they don't have any, like, backing about it being organic or non-GMO or whatever. They just said, you know, it's the local sources process or whatever through them. So I'll go back and look at the email communication I had with them and see how we're gonna utilize it.
Okay.
Yeah, they're not real helpful, but they are the predominant manufacturer in the U.S. So
There are providers who get really hung up on that.
yeah, I know
No,
it's
I'm not reacting to the Roundup, you know.
yeah, but the reality is how much Roundup is in the carrot sample.
I agree. But
And yeah,
that's
it's
what a provider wants to focus on. That's
Yeah.
gonna be their focus. You know?
I know, yeah, it is a hang up, and our the original food profile that we came out with in I think 2010, 2011 had like polysorbate 80 and preservatives and red dyes, and it's like, well, how much red dye or yellow dye is really in the Twinkie compared to the amount of gluten and you know, the other icky things that are in there. So you might have some reactivity, but from an immunological point of view, the hierarchy, there is a hierarchy of things that your body likes to make an immune response to. First thing is proteins. Body loves proteins. That's what viruses are made out of. Viruses, bacteria, icky things are proteins. Ironically, I was a little surprised by this one. Number 2 is carbohydrates. The reason I'm drawing this out this way is, for lack of a better phrase, for immunology, size and complexity matter. So it's all about size. Proteins are large. They're complex because there's 20, well, depending on what you look at, there's 20 plus amino acids if you look at all the different isoforms. So they're large, they're complex. Carbohydrates are also large, or can be. They have a lot less complexity, but the thing about carbohydrates, and then these are also usually can be charged on proteins, because amino acids have charge. You have positive and negative charges. Carbohydrates are large, but they're not really complex and they're not really charged. But they're big. Lipids, I mean fats, things like cholesterol, but LPS is lipopolysaccharide, so it's a lipid and a saccharide that your body makes an immune response to. Fourth thing would be your small molecules. Your small molecules they're kind of boring to the immune system because from an immunological point of view, your body will make an immune response to 6 amino acids. It'll take some like HIV protein or hepatitis, cleave up that protein into a bunch of little pieces that are about 6 amino acids in size. So when you talk small molecules, the small molecules are smaller than those 6 amino acids, so your body just really doesn't see them. So that's kind of the pesticide thing, is that they're small organic molecules, they're bad, but at the same time your body doesn't make an immune response to benzene. Benzene is nasty in its own right because of other things. Your body doesn't make an antibody response to cholesterol or to hormones. It'll make responses to the hormone receptor, which is a protein, but not to the hormone itself. Unless you have there are specific proteins that'll bind small molecules in your body, but they're designed to do that. Tangent. And so, any other questions over? But yeah, that's the hierarchy of immunogenicity. And in order to get this to happen, they actually, in a laboratory point of view, you have to do a lot of work to get an animal or something to respond to that. You can't just inject polysorbate 20 into a rabbit and get an immune response.